Look up at the night sky. What you see, the glittering stars, the glowing galaxies, the vast cosmic tapestry, is only half the story. Billions of years ago, the universe looked nothing like this. It was a silent sea of darkness, a cold and neutral fog where light could barely travel. And then something happened, something profound, something mysterious, something that lit up the cosmos and set the stage for everything we know. What was it that transformed our universe from that primordial darkness into the brilliant, ionized expanse we observe today? This is the great cosmic mystery. We're about to explore the era of reionization, a chapter in the universe's adolescence that remains one of astronomy's most compelling and elusive puzzles. It's a story written in the ancient light of quasars, echoed in the faint whispers of the first galaxies, and waiting to be uncovered by the most powerful telescopes ever built. We're going to journey back in time, not just millions but billions of years, to an epoch when the universe was raw, young, and brimming with change. This was the Cosmic Reionization Era, a period so transformative that it shaped the fate of the cosmos itself. Yet for all its importance, it's a time we understand only in fragments, a cosmic detective story with clues scattered across space and time. How did the first stars and galaxies flood the universe with light? What forces ripped apart the neutral hydrogen that filled the early cosmos? And why does this era still challenge everything we think we know about how structure formed in the universe? These aren't just academic questions, they lie at the very heart of our quest to understand where we came from and how the universe grew up. In this video, we'll uncover 25 mind-bending mysteries surrounding the reionization era, each one a piece of the puzzle, each one raising new questions about the nature of the early cosmos. From the role of the very first supermassive black holes to the puzzling behavior of faint, distant galaxies, from the lingering shadows of the cosmic dark ages to the cutting-edge observations that are rewriting the textbooks, this is a journey to the edge of our understanding. You'll come away not only with a deeper appreciation for how our universe evolved, but with a sense of wonder at just how much remains unknown. So let's begin. Our journey into the Cosmic Reionization Era begins with its most fundamental mystery. Where did the very first light come from? Picture the universe at this point. It's around 400 million years old, and it's still shrouded in that primordial fog of neutral hydrogen gas. Then, a spark. The first photons with enough energy to rip electrons away from their atoms begin to fly through the cosmos. But what cosmic object flickered on first to produce that spark? This isn't just a question of what came first. It's about identifying the primary engine that drove the entire reionization process, and astronomers have several compelling suspects. The leading candidate for decades has been population 3 stars. These aren't the stars we see today. Theorized to be the very first generation, they were behemoths, hundreds of times more massive than our Sun. They would have lived fast and died young, burning ferociously hot and flooding their surroundings with immense amounts of the exact kind of ultraviolet light needed to ionize hydrogen. Their spectacular supernova deaths would have also seeded the early universe with the first heavy elements, fundamentally changing its chemical makeup. The challenge is we've never definitively observed one. They remain ghosts in the cosmic machine, their existence inferred from models but not yet confirmed by direct evidence. Another fascinating suspect is a class of objects known as direct collapse black holes. The theory suggests that in the incredibly dense early universe, vast clouds of pristine gas could have collapsed under their own gravity, not into a star but directly into a supermassive black hole. These black holes, feasting on the surrounding gas, would have become incredibly luminous quasars, pouring out torrents of ionizing radiation. While we have discovered a few stunningly bright quasars from this epoch, they seem too rare to have done the job all by themselves. They might have been the powerful blowtorches in a few key areas, but were they the universal workhorses? This leads us to the third and perhaps most likely culprit: early galaxies. Not necessarily the titanic ones we see later, but vast populations of small, faint, and incredibly active dwarf galaxies. Think of them not as single brilliant beacons, but as a massive cosmic crowd, each contributing a small amount of ionizing radiation. Together, their collective output could have been more than enough to flood the universe with light. The puzzle here is that much of this critical ionizing radiation might have been trapped within these galaxies by their own gas and dust, preventing it from escaping to do its job on the intergalactic medium. This is where the James Webb Space Telescope is revolutionizing the investigation. Its unprecedented power allows it to peer back to the very dawn of galaxy formation, looking for the faint signatures of these first light sources. Webb isn't just looking for the objects themselves, it's searching for the telltale leaks. By analyzing the spectrum of light from these ancient galaxies, astronomers can now detect the specific signatures of ionizing radiation actually escaping their galactic boundaries. Early results are already hinting that the answer might not be one single culprit, but a complex cosmic consortium where population 3 stars, early galaxies, and perhaps even those direct collapse black holes all played a part in different ways and at different times, weaving together to illuminate the cosmos. If pinpointing the first light is difficult, establishing a universal timeline for this entire era has proven even more elusive. We call it the Cosmic Reionization Era, but that implies a single, clean event with a defined beginning and end. The reality, as astronomers are discovering, was far messier and much less uniform. When exactly did this grand transformation start? How long did it take? And did it happen everywhere at once? The evidence we've gathered paints a conflicting and deeply puzzling picture, suggesting our universe didn't flip a switch from dark to light, but rather stumbled towards illumination in fits and starts. Some of our most crucial clues come from the oldest light we can observe, the cosmic microwave background. This afterglow of the Big Bang holds a subtle imprint of the reionization process. When the first photons began to ionize the hydrogen fog, they would have scattered off the newly freed electrons. This scattering left a distinct mark on the polarization, or the orientation, of the microwave background radiation. Satellite missions like Planck have studied this polarization in exquisite detail, and their data suggests that reionization was a relatively quick affair, likely complete by the time the universe was around 1 billion years old, a point we astronomers refer to as a redshift of about 6. This paints a picture of a swift and decisive cosmic revolution, but when we look at a completely different set of clues, that neat timeline begins to unravel. Our window into this later period comes from quasars, the incredibly bright cores of distant active galaxies. As their light travels billions of light years to reach us, it passes through clouds of intergalactic hydrogen. Neutral hydrogen gas is very good at absorbing specific wavelengths of this light, creating a telltale pattern of dark lines in the quasar spectrum known as the Lyman alpha forest. By studying quasars at different distances, and therefore from different times, we can observe how these absorption lines change. The startling finding is that even at redshifts below 6, we still find patches of stubbornly neutral hydrogen. This indicates that some regions of the universe held onto their primordial fog for longer than others, implying the process was more gradual and protracted than the microwave background suggests. So which evidence do we trust? Is the cosmic microwave background wrong, or are the quasar studies misleading? The most compelling resolution to this contradiction is that both are right in their own way. Reionization was not a synchronized event across the cosmos. Instead, it was a patchwork process. Imagine a vast landscape at dawn. The first peaks of mountains catch the sunlight first, while the deep valleys below remain shrouded in shadow for much longer. In the early universe, the first galaxies and quasars acted like those mountain peaks, creating expanding bubbles of ionized gas around themselves. These bubbles gradually grew and merged, but the process was uneven. Denser regions of the universe with more galaxies would have reionized first. Vast, emptier voids might have remained neutral for hundreds of millions of years longer. This cosmic patchwork makes it incredibly difficult to assign a single date to reionization's end. The universe didn't have a single moment of full illumination. It had a final valley that was the last to see the light. This patchwork process leads us directly to our next great mystery. What exactly happened to all that neutral hydrogen? If you think of the universe before reionization as a vast, dark ocean, then the first light sources were like heated stones dropped into that water, creating bubbles of steamy, ionized plasma. But what was the fate of the water itself? The story seems simple. The light came, the fog cleared. But the evidence we have tells a far stranger and more complicated tale, one that has astronomers questioning their most sophisticated simulations. It's a cosmic magic trick we're still trying to figure out, the Great Hydrogen Disappearance Act. Our best tools for understanding this process are immense computer simulations. Astronomers create virtual universes inside supercomputers, programming in the known laws of physics and then populating them with simulated galaxies and quasars. They let these digital cosmos run for billions of simulated years to see if they produce a universe that looks like our own. When it comes to reionization, these simulations make a specific prediction. As the ionizing radiation floods out, it should carve the neutral hydrogen into a very distinct structure. We should see a predictable pattern, a cosmic Swiss cheese, where the holes are the expanding ionized bubbles and the remaining cheese is the shrinking network of neutral hydrogen filaments and clouds. According to many models, this neutral material should have been almost entirely eradicated by the end of the reionization era, leaving behind only a few faint wisps. But when we look at the real universe through our telescopes, that's not what we see at all. Our primary window into this is the Lyman alpha forest we mentioned earlier. The light from a distant quasar is like a brilliant flashlight shining through the cosmic woods. Every tree it passes through, every cloud of neutral hydrogen absorbs a specific part of its light, leaving a dark line in its spectrum. The sheer number of these absorption lines creates a dense forest, and by mapping this forest in quasars from different eras, we can create a timeline of how the neutral hydrogen thinned out. The shocking revelation is that this forest is far richer and more persistent than most simulations predicted. Neutral hydrogen didn't just vanish, it hung around in vast, complex structures for much longer than anyone expected. It's as if we simulated a fire burning through a dry field and predicted a clean sweep of ash, but when we look, we still find countless patches of unburned grass. This contradiction points to a fundamental gap in our understanding. Perhaps the early galaxies weren't efficient enough at producing and releasing their ionizing radiation, leaving countless shadows and sheltered valleys where hydrogen could remain neutral. Maybe the distribution of gas in the early universe was far lumpier and more complex than our models assume, creating dense pockets that could shield themselves from the incoming radiation. There's even the fascinating possibility that the process of reionization itself constantly stirred up the hydrogen, causing it to clump together in new ways that made it more resilient, a case of the cure altering the patient in unpredictable ways. The deepest part of this mystery involves the most stubborn survivors of all, the so-called Lyman limit systems and damped Lyman alpha absorbers. These are not just wispy clouds, they are dense, colossal reservoirs of neutral gas, so thick they can completely block ionizing radiation. Astonishingly, we find these gigantic, primordial blobs of neutral hydrogen existing long after reionization was supposedly over, some persisting for billions of years. Their continued existence is a direct challenge to the idea of a swift and total universal transition. They are living fossils, relics of the cosmic dark ages that somehow weathered the storm of ionizing photons, and their survival forces us to rewrite the narrative of how our universe cleared its throat. The hydrogen didn't just disappear, it staged a gradual, reluctant, and deeply uneven retreat, and we are still mapping its final hiding places. Even as we map the haphazard retreat of the hydrogen, a far more fundamental problem emerges, one that strikes at the very heart of our understanding of this era. We've identified the suspects and we've seen the uneven results of their work, but when we actually sit down to do the cosmic accounting, the numbers simply don't add up. This is the source efficiency conundrum, a glaring deficit in the universal photon budget that forces us to ask a startling question. Did we even identify the right criminals for this cosmic crime? Think of it like this: to ionize a single atom of hydrogen, you need just one photon of ultraviolet light with enough energy. But the early universe was an incredibly vast and densely packed place, filled with trillions upon trillions of hydrogen atoms. To rip them all apart, you would need a correspondingly immense number of these ionizing photons, a veritable flood of ultraviolet light. Astronomers have crunched the numbers to calculate this required photon budget, estimating how many of these specific photons needed to be produced, and more importantly, to successfully escape their sources and travel through intergalactic space to do their job. Now we take inventory of the known sources we can actually observe from that time. The incredibly bright quasars, while powerful, are far too rare. Their collective output is a mere drop in the bucket. The larger, more obvious galaxies we can see with telescopes like Hubble also fall woefully short. Even when we add their theoretical contributions together, we are left with a massive shortfall. There simply aren't enough visible factories producing enough ionizing light to power the entire reionization of the cosmos. It's as if we're trying to light up an entire continent with nothing but a few scattered flashlights. The math just doesn't work. This glaring gap between what was needed and what we can plainly see is one of the most persistent puzzles in modern cosmology. So where did all the missing light come from? Astronomers are exploring several compelling, and in some cases revolutionary, solutions. The first and most promising idea is that we are dramatically underestimating the number of faint dwarf galaxies. Our telescopes, even the magnificent Hubble, have primarily been able to see the tip of the cosmic iceberg, the biggest and brightest galaxies from the early universe. But what if the true workhorses of reionization were trillions of incredibly faint small galaxies, a vast unseen population whose collective light would be enough to fill the budget? This is where the James Webb Space Telescope is already making waves. Its infrared eyes are peerless at detecting these faint, redshifted objects, and its early observations suggest the early universe was indeed teeming with far more of these tiny galaxies than our best models had predicted. They may be the missing workforce, the invisible legion that did the heavy lifting. The second possibility is that the galaxies we can see are far more efficient than we thought. A critical number in this equation is called the escape fraction. This is the percentage of ionizing photons a galaxy produces that actually manages to escape its gaseous confines, rather than being absorbed by its own internal clouds of dust and hydrogen. For decades, models assumed this fraction was quite low, perhaps only 5 to 10%. But what if it was much, much higher in the early universe? These primordial galaxies were different. They were smaller, more turbulent, and lacked the heavy elements that help trap light. Recent observations from Webb are already hinting at some early galaxies with escape fractions of 50% or even higher. If that was common, it would completely rewrite the budget, turning each known galaxy from a dim bulb into a brilliant spotlight. And then there is the most thrilling possibility of all, that there were entire classes of exotic objects present in the early universe that we have not yet even dreamed of. Perhaps there were unstable, supermassive stars unlike anything we see today, or bizarre phases of black hole accretion that poured out unimaginable amounts of energy. Maybe the dark matter itself, which makes up most of the universe's mass, interacted in ways we don't understand, producing radiation. While this seems like the stuff of speculation, the profound disconnect between what we need and what we see forces us to keep these extraordinary ideas on the table. The photon budget doesn't lie. It is a cold, hard accounting of a universal revolution, and right now, the books are not balanced, pointing toward a cosmos that still holds profound secrets about its own awakening. But while hydrogen was the main character in the story of reionization, it wasn't the only element in the cosmic fog. There was another, more stubborn player hiding in the shadows: helium. The universe's second lightest element makes up a significant portion of the normal matter created in the Big Bang, and its reionization presents a separate, and in some ways even more baffling, cosmic riddle. To understand why, we have to appreciate a key difference in their atomic structure. While a hydrogen atom has just one electron to strip away, a helium atom holds onto its two electrons with a much tighter grip. It takes a far more energetic photon, one from the extreme ultraviolet or even soft X-ray part of the spectrum, to rip that first electron free and singly ionize helium. And to remove the second electron and fully ionize it, that requires a staggering amount of energy, nearly 4 times more than what was needed for hydrogen. This fundamental difference in physics means the story of helium's reionization had to be written by a completely different kind of author. The first stars and small galaxies, powerful as they were, simply didn't produce enough of this high-energy radiation. Their ultraviolet light was perfect for hydrogen, but it barely made a dent on helium. The only cosmic objects capable of generating the required torrent of hard photons were the incredibly brilliant, intensely energetic cores of active galaxies, quasars, powered by supermassive black holes greedily accreting vast amounts of material. So, if hydrogen reionization was a populist uprising led by countless small galaxies, helium reionization was a specialized operation conducted by a few incredibly powerful elite agents. The evidence for when this happened comes from a technique similar to the one used for hydrogen. Astronomers look at the light from distant quasars, but instead of searching for absorption by neutral hydrogen, they hunt for a specific signature of singly ionized helium. When this helium is present in intergalactic clouds, it absorbs light at a very specific wavelength. By observing quasars at different distances, we can trace when these absorption features disappear, indicating that the helium in the vast intergalactic regions has been fully ionized. The data points to a clear conclusion. The universe-wide reionization of helium occurred much later, when the cosmos was around 2 billion years old, a point we mark as a redshift of about 3. And this is where the true mystery deepens. Why did it take so long? If the quasars were there and they had the power, why was there a gap of nearly 1 billion years between the completion of hydrogen reionization and the start of helium's? It's a profound cosmic delay that has astronomers scratching their heads. One compelling theory is that it simply took that long for the quasar population to reach its peak. The supermassive black holes that power quasars needed time to grow to immense sizes through mergers and accretion. Perhaps it wasn't until redshift 3 that there were enough truly monstrous black holes actively feeding to flood the universe with the required radiation. Another fascinating possibility involves the changing architecture of the universe itself. In the earlier, denser universe, the very gas that quasars needed to feed on might have been too abundant, actually stifling their growth by choking their accretion disks. Alternatively, the process might have been hampered by the distribution of the helium itself. Maybe the helium was clustered in regions that were harder for the quasar light to reach. Or perhaps the ionizing photons themselves were being absorbed by other elements along the way, creating a kind of cosmic traffic jam that slowed the entire process down. The late reionization of helium remains a crucial piece of the puzzle, a reminder that the universe's transition from darkness to light was not one event, but a series of complex, overlapping chapters, each with its own unique trigger and timeline. Just when we think we're beginning to map the universe's transformation, another layer of complexity emerges, forcing us to re-examine our most basic assumptions. If the clearing of the cosmic fog was uneven and its photon budget remains unbalanced, then what happened to the energy itself? This brings us to a thermal mystery, a puzzle written not in light or darkness but in heat. After the flood of ionizing radiation did its work, it didn't just vanish. Its energy had to go somewhere. It was absorbed by the very gas it had just torn apart, and that absorption had a profound and lasting effect. It heated the entire intergalactic medium to incredible temperatures. For decades, cosmologists have run sophisticated simulations predicting just how hot this universal heating should have been. But when they compare those predictions to actual measurements of the ancient cosmic gases, the numbers are startlingly mismatched. The universe, it seems, ran a far higher fever than anyone ever expected. To measure the temperature of gas billions of light years away and billions of years in the past, astronomers use a remarkably clever technique involving the very same Lyman alpha forest we discussed earlier. Think of each absorption line in a quasar's spectrum as not just a marker of neutral hydrogen, but as a tiny thermometer. The width of each absorption line is directly related to the motion of the hydrogen atoms themselves. In hotter gas, atoms zip around at higher speeds, and this Doppler broadening smears out the absorption line, making it wider. By meticulously analyzing the precise shapes and widths of thousands of these lines from quasars at a specific redshift, scientists can calculate the average temperature of the intergalactic gas at that specific chapter in cosmic history. It's an indirect measurement, but an incredibly powerful one, giving us a readout of the universe's temperature over billions of years. What these cosmic thermometers tell us is that the gas was scalding hot and remained so for a surprisingly long time. The most advanced computer models of reionization predicted that the intergalactic medium would have been heated to temperatures of around 20,000 degrees Celsius already, an unimaginable heat. Yet the observational data consistently points to temperatures far higher, perhaps by an additional 10 to 20,000 degrees. This isn't a minor discrepancy, it's a massive energy surplus that demands an explanation. Where did all this extra heat come from? The initial burst of ionizing photons from the first stars and galaxies should have provided a specific, calculable amount of energy. Something else must have been pumping additional energy into the system, like a hidden furnace stoking the fires of the early cosmos. This unexpected heat has led theorists to propose some fascinating additional heating mechanisms. Perhaps the reionization process itself was more violent and explosive than we've assumed. If the first stars were predominantly the monstrous population 3 stars, their deaths in pair instability supernova would have been cataclysmic events, orders of magnitude more energetic than later supernova, potentially flooding their surroundings with shock waves that heated the gas far beyond the effect of mere photons. Another compelling idea involves the hard radiation from those early quasars and active black holes. Their high-energy X-rays can travel vast distances through space before being absorbed, and when they finally are, they deposit their energy as heat much more efficiently than ultraviolet light, providing a pervasive and uniform heating mechanism that could account for the extra temperature. The implications of this intergalactic heat wave are profound and extend far beyond the reionization era itself. The temperature of the cosmic gas plays a critical role in the fate of the universe's future structures through a concept known as Jean's mass. Simply put, hotter gas has higher pressure, which makes it much harder for gravity to collapse it to form new galaxies. If the gas is too hot, small, delicate density fluctuations simply get smoothed out and erased, preventing the formation of smaller dwarf galaxies. This universal heating essentially set a cosmic minimum size for galaxy formation, effectively putting a floor on how small a galaxy could be. The unexpected extra heat we see suggests this floor was higher than we thought, meaning a whole population of potential small galaxies may have been suppressed, forever altering the demographic landscape of the cosmos we see today. This thermal mystery is ultimately a story about feedback, one of the most important and complex concepts in cosmology. The first light sources didn't just illuminate the universe, they fundamentally changed its physical state, and that change, in turn, dictated what could form next. The energy output from the first stars and black holes created an environmental feedback loop that governed the pace and pattern of all future cosmic evolution. The fact that this feedback appears to have been more energetic than we predicted forces us to reconsider the true power and influence of those first cosmic engines. Their legacy isn't just written in the light we see, but in the lingering heat we measure, a thermal echo of a revolution that shaped the universe forever. This intricate dance between creation and destruction brings us to one of the most fascinating and self-referential puzzles of the era: the galaxy formation feedback loop. We often imagine the first galaxies as heroic pioneers, bravely shining their light into the darkness. But what if that very act of heroism made it impossible for their neighbors to do the same? This is a classic cosmic chicken and egg scenario where the process of reionization, driven by galaxies, fundamentally altered the environment in which new galaxies could form, potentially choking off the very process that started it all. To understand this loop, picture a young, vigorous galaxy. It's furiously forming massive hot stars that flood its local region with ultraviolet light. This radiation doesn't just travel outward to ionize the cosmic fog. It also violently heats the vast reservoirs of cool, neutral hydrogen gas that are swirling in and around the galaxy itself. This is the raw fuel for future star formation. Stars are born when dense, cold clouds of this gas collapse under their own gravity. But when that gas is heated by intense radiation, it gains pressure. Think of it like trying to compress a hot air balloon. It fiercely resists being squeezed. This heated gas simply cannot collapse to form new stars. So, by shining its light, a galaxy effectively sterilizes its own immediate surroundings, putting a ceiling on its own growth and preventing smaller, nascent galaxies nearby from ever getting started. This is negative feedback in its purest form, a self-regulating mechanism where a galaxy's brilliant success leads directly to its own limitations. If this negative feedback were the whole story, the era of reionization might have been incredibly brief. A brilliant flash followed by a swift return to darkness as the first galaxies shut down further star formation across the cosmos. But that's clearly not what happened. The universe kept making stars and galaxies, so the pressing mystery is not just that feedback occurred, but how so many galaxies managed to circumvent their own self-imposed shutdown. How did star formation not only continue but apparently thrive, building the larger galaxies we see today? The answer seems to lie in a bizarre cosmic inequality, where only galaxies with special advantages could weather the storm they helped create. One major advantage was simply location. In the densest knots of the cosmic web, where dark matter and gas were piled deep, gravity was an overwhelmingly powerful force. Here, the relentless pull towards collapse could potentially overpower the outward pressure from the heated gas. A proto-galaxy in such a rich environment could have been massive enough to literally hold onto its cool gas reservoir, shielding it from the external radiation and continuing to form stars in its core, almost oblivious to the inferno raging outside its borders. These cosmic metropolises became the survivors, their growth fueled by the sheer density of their birthplaces. Another crucial factor was a galaxy's ability to constantly replenish its fuel supply. Imagine a galaxy that can't just rely on its initial store of gas, but has a steady pipeline delivering fresh, cool hydrogen from the intergalactic medium. This isn't just theoretical. Gas flows along the faint filaments of the cosmic web, funneling new material into galaxies. A galaxy positioned at the intersection of several of these cosmic rivers could have enjoyed a continuous inflow of pristine fuel. This constant replenishment might have allowed it to sustain star formation even as some of its gas was being heated and blown away, essentially outrunning the negative feedback by always having more cool gas arriving. It's like trying to put out a fire with a steady stream of water while someone else is trying to fan the flames. The inflow can win. Then there's the role of violence and chaos. The early universe was a turbulent place, and galaxies were not the serene spirals we see today. They were chaotic, messy, and prone to massive collisions. When two small galaxies merged, the event would have violently compressed their combined gas reservoirs, potentially triggering intense, explosive bursts of star formation all at once. This starburst could be so rapid and powerful that it floods the local region with ionizing radiation before the feedback process has any time to react and shut it down. In this scenario, galaxies didn't avoid the feedback. They essentially raced through it, accomplishing a lifetime of star formation in a breathtakingly short period, like a cosmic flash in the pan that was over before the surrounding gas could even heat up. Unraveling this feedback loop is more than an academic exercise. It's key to understanding the demographics of our modern universe. The balance between negative and positive feedback processes in these first few billion years determined the final size distribution of galaxies. It decided how many giant ellipticals and grand spirals we would have, and how many countless dwarf galaxies failed to form or were stripped of their gas, becoming mere ghosts. The feedback from reionization didn't just clear a fog. It acted as a cosmic while the dance of light and matter shaped the visible universe. An invisible architect was directing the entire performance from the shadows. To truly understand reionization, we must confront its most enigmatic player, dark matter. This mysterious substance, which makes up about 85% of all matter in the cosmos, cannot be seen because it doesn't emit, absorb, or reflect light. Yet its gravitational pull is the fundamental force that built the cosmic stage upon which reionization played out. Without dark matter, there would be no galaxies, no stars, and no story of cosmic awakening to tell. Its role, however, is far from understood, and the specific properties of this elusive material might hold the key to some of the era's most stubborn mysteries. The standard model of cosmology, known as the lambda cold dark matter model, provides our foundational script. In this story, dark matter is cold, meaning its particles moved sluggishly in the early universe. This allowed it to quickly collapse under its own gravity, forming an immense, invisible scaffolding called the cosmic web. Vast halos of dark matter grew at the intersections of this web, and their immense gravitational wells acted as traps, pulling in the normal hydrogen and helium gas. It was within these dark matter halos that the gas could become dense enough to fragment, collapse, and eventually ignite into the very first stars and galaxies. In this view, dark matter was the passive but essential real estate developer, creating the neighborhoods where the luminous actors of reionization could reside. The timing and pattern of reionization were therefore set by the growth rate of these dark matter structures, where the largest halos formed first, creating the first and brightest sources of light. But what if dark matter isn't cold? This is where the plot thickens considerably. A compelling alternative theory suggests dark matter could be warm. Warm dark matter particles would have been zipping around at much higher speeds in the early universe. This frenetic motion would have prevented them from collapsing into very small clumps, effectively erasing the smallest wrinkles in the cosmic fabric. The consequence for reionization would be profound. A warm dark matter universe would lack a vast population of tiny dwarf galaxies, as the small dark matter halos needed to host them would never form. Without these countless faint sources, reionization would have to be driven by fewer, larger, and later forming galaxies. This would significantly delay the entire process and create a much more uneven, patchy reionization timeline, potentially aligning better with some of our conflicting observational data. The nature of dark matter, whether cold or warm, isn't just a technical detail. It directly dictates the cast of characters available to light up the cosmos. The mysteries deepen even further when we consider that dark matter might have been more than just a gravitational stagehand. What if it played an active, dynamic role in the reionization process itself? This idea ventures from the standard model into the realms of theoretical physics, but it's a possibility that scientists are seriously exploring to explain the universe's unexpected heat and the puzzling photon budget. Certain exotic models propose that dark matter particles could interact with each other through forces other than gravity. These self-interactions could cause them to annihilate when they collide, converting their mass directly into energy and producing a flash of radiation, including high-energy photons that could contribute to ionization. If this were happening within the dense cores of the first dark matter halos, these invisible regions could have been secret power plants, flooding the early universe with an additional, hidden source of ionizing radiation. Another fascinating, though highly speculative, idea involves dark matter interacting not with itself, but with the regular matter we know, so-called decaying dark matter. Models suggest that what we think of as a stable particle might actually be slowly disintegrating over cosmic time. The decay products could include particles that deposit energy into the intergalactic gas, providing that mysterious extra heating that our measurements reveal. This would mean the scalding temperature of the post-reionization universe wasn't just caused by stars and quasars, but was also being subtly stoked by the invisible and gradual unraveling of the cosmos's dominant form of matter. While evidence for these active dark matter scenarios remains elusive, their potential to solve multiple reionization puzzles with a single, elegant mechanism makes them a thrilling area of ongoing research, reminding us that the darkest parts of the universe might hold the brightest sparks of discovery. But if the cosmic web provided the architecture for reionization, the precise pathway the light took through that labyrinthine structure is one of the most heated debates in modern cosmology. This is the mystery of topology. Did ionization spread from the inside out or the outside in? It's a question that gets to the very heart of how energy moved through the primordial universe, and the answer is far from settled. The inside-out model has long been the favored story. It's an intuitive and elegant idea. The first galaxies igniting within the deepest, densest knots of the cosmic web would have created brilliant, expanding bubbles of ionized plasma around themselves. As these bubbles grew, they would have first merged with their immediate neighbors within the same dense filament, effectively turning the entire backbone of the cosmic web into a glowing network of light. Only after the filaments were fully illuminated would these bubbles have finally expanded outward into the vast, empty voids. In this scenario, the densest regions are the pioneers, and the voids are the last territories to be conquered. Yet a compelling and counterintuitive alternative has emerged, the outside-in model. This theory suggests that the lowest density voids might have actually reionized first. How could that possibly work? The key lies in the nature of the radiation sources and the opacity of the gas. In the dense filaments and knots, the gas is thick and crowded. While there are more galaxies producing more ionizing photons, those photons have a very short mean-free path. They don't travel far before slamming into a hydrogen atom and being absorbed. The voids, however, are almost empty. A single photon emitted from a galaxy on the edge of a void could travel staggering distances through that near vacuum, ionizing a vast volume of space with very little resistance. In this view, the reionization of the voids isn't a slow, final push. It's a rapid and efficient process that happens early on, while the dense filaments, choked with their own gas, lag behind and are the last to become fully transparent. Future observations, particularly with a powerful new type of astronomy, promise to finally settle this debate. The most exciting tool on the horizon is the detection of the redshifted 21-centimeter line. Neutral hydrogen gas naturally emits a faint radio signal at a wavelength of 21 centimeters. by building massive radio telescope arrays to map the universe at different frequencies which correspond to different distances and thus different cosmic epochs. Astronomers will be able to create a three-dimensional movie of the reionization process. We won't just see a blurry before and after picture. We will watch the neutral hydrogen disappear in real time across billions of light years. The first images from prototypes of these telescopes are already revealing a universe that is far more complex and bubbly than any single model predicted. They show a patchwork of ionized and neutral regions that doesn't perfectly match either the inside-out or outside-in scenario, but rather a chaotic mixture of both, suggesting that the topology of reionization was not a simple, uniform process, but a deeply local and messy one, dictated by the unique arrangement of galaxies and gas in each region of the cosmos. Even with a universe potentially teeming with faint galaxies, a more fundamental obstacle emerges, one that strikes at the very physics of how a galaxy operates. We call this the Lyman continuum escape problem, and it's arguably the single greatest bottleneck in our entire understanding of reionization. The name sounds technical, but the concept is simple yet profound. It doesn't matter how many ionizing photons a galaxy produces if they can't actually get out the door. A galaxy could be the most brilliant ultraviolet factory in the cosmos, but if that light is trapped behind walls of its own gas and dust, it's useless for the grand task of clearing the universal fog. The key number here is the escape fraction, the tiny percentage of these powerful photons that actually manages to flee a galaxy's gravitational grasp and travel into intergalactic space. When we look at galaxies in our modern, local universe, the escape fraction is almost laughably small. In typical spiral and dwarf galaxies nearby, observations suggest that less than 1%, often far less, of their ionizing radiation ever makes it out. The vast majority of these photons are almost immediately absorbed by the dense clouds of hydrogen, gas that swirl within the galaxy's own disk and halo. They are absorbed and then re-emitted at lower, safer energies, their ionizing power neutered before they can even reach the border. If the first galaxies were anything like their modern counterparts, reionization would have been impossible. The math is brutally clear. The early universe required escape fractions of at least 10, 20, or even 50% to get the job done. So the pressing mystery is not just what produced the photons, but what kind of bizarre galactic architecture allowed them to stream out into the cosmos so efficiently. Solving this puzzle means understanding the intricate journey a single photon must take from its birth to cosmic freedom. It begins its life in the intense heat of a massive star's atmosphere. From there, it must travel through the star's own local environment, often a dense stellar nursery packed with gas. It then has to navigate the wider interstellar medium of the galaxy, a complex maze of molecular clouds, hydrogen filaments, and dusty nebulae. The slightest encounter with a neutral hydrogen atom will end its journey instantly. For a photon to escape, it needs a nearly clear path, a channel of pre-ionized or very low-density gas that stretches all the way from the star-forming region to the edge of the galaxy. Creating and maintaining these channels is the central challenge, and astronomers are investigating several powerful mechanisms that could have ripped them open in the early universe. One of the primary suspects is the raw, unbridled violence of stellar feedback. The first stars, particularly the hypothetical population 3 giants, would have been ferocious objects. Their immense radiation pressure alone could have pushed away the surrounding gas, carving out vast bubbles of ionized plasma within their natal clouds. Their deaths in colossal supernova explosions would have been even more effective, blasting out shock waves that could sweep up neutral gas, clear out huge cavities, and even punch holes directly through the galactic disk. These stellar winds and supernova essentially act like cosmic jackhammers, breaking open escape routes for the photons produced by the next generation of stars. In this turbulent environment, a galaxy might temporarily resemble a leaky sieve, with fountains of ionizing radiation pouring out through these freshly made chimneys. Another potent mechanism is the sheer dynamism of the early cosmos itself, particularly the role of galaxy mergers. The first galaxies were not the stable, ordered spirals we see today. They were small, irregular, and constantly smashing into each other. These collisions are incredibly disruptive events. They can trigger massive, centralized bursts of star formation, but they can also violently stir up a galaxy's gas, flinging it outwards or even ejecting it entirely in tidal tails. This gravitational chaos could have effectively shredded the dense gas clouds that normally trap radiation, creating a brief but incredibly productive window where the escape fraction skyrockets. A merging galaxy might temporarily become a brilliant beacon, its light unleashed by the very violence of its collision. The greatest frustration for astronomers is that this critical process is devilishly difficult to observe directly. We cannot see these escape routes with our telescopes. The photons that escape are, by definition, the ones we don't see being absorbed within the galaxy. The neutral hydrogen that blocks them is also largely invisible. It's like trying to study the architecture of a maze by only looking at the people who successfully exit. You have to infer the structure of the walls from the paths of those who made it out. The James Webb Space Telescope is now offering our first real glimpses into this process by studying galaxies at the precise epoch of reionization. Astronomers are not just looking for the light these galaxies emit, but for specific telltale signatures in their spectra that indicate a high escape fraction, such as a strong ratio of certain ionized gas lines. Early data is tantalizing, suggesting that some of these ancient galaxies do indeed show evidence of being porous, with signs of vigorous outflows and channels that could have let the light flow free. Each confirmation brings us closer to understanding how the first galaxies solved their own great escape, breaking free from their gaseous prisons to illuminate the universe. Yet for all the power of starlight, there was another class of cosmic object capable of flooding the universe with an even more intense and penetrating form of radiation, and its true role in the reionization story remains one of the most contentious debates in astrophysics. This is the quasar contribution controversy, a mystery that pits the brilliant few against the invisible many. On one side of the argument, the evidence seems overwhelmingly clear. The incredibly bright classic quasars we have found from the reionization epoch are far too rare to have been the primary drivers of this universal transformation. These are the behemoths, the supermassive black holes with masses billions of times that of our Sun, actively devouring gas and shining with the brightness of a trillion stars. They are undeniably powerful, each one a colossal engine of ionization. But when you count them up across the early universe, their numbers just don't add up to the required photon budget. They are the flashy celebrities in the cosmic story, but there simply aren't enough of them on the red carpet to light up the entire theater. The core of this argument lies in the sheer scale of the task. To reionize the entire cosmos, you need a distributed network of power plants, not just a few scattered megacities. The bright quasars are those megacities, incredibly luminous but separated by vast, dark distances. Statistical surveys from telescopes like Hubble and now Webb have mapped their population, and the math consistently shows that even if every single ionizing photon they produced escaped into intergalactic space, it would only account for a small fraction of the necessary energy. Their contribution, while vital in their immediate vicinity, was likely limited to creating some of the very first and largest ionized bubbles around themselves, acting as brilliant but isolated lighthouses in a still dark sea. They were the pioneers, but not the main workforce. This has led many astronomers to largely dismiss quasars as major players, focusing their attention instead on the collective might of those countless faint galaxies. But a fascinating counter-argument has been gaining traction, one that suggests we may have been looking for the wrong kind of quasars. What if the early universe wasn't dominated by the rare, brilliantly shining monsters, but by a hidden population of faint quasars or rapidly accreting black holes. These wouldn't be the titans we easily spot, but a much larger population of smaller, hungrier black holes, perhaps the precursors to the supermassive ones we see later. In this scenario, it's not about the power of each individual source, but about their overwhelming numbers. A universe teeming with millions of these faint, actively feeding black holes could collectively produce a staggering amount of ionizing radiation, potentially solving the photon budget problem from an entirely different direction. The challenge has always been finding them. These faint quasars are, by definition, extremely difficult to detect at such incredible distances. Their light is drowned out by the glare of their host galaxies and stretched into the deep infrared by the expansion of the universe. This is where the James Webb Space Telescope is completely changing the game. Its infrared sensitivity is unparalleled, allowing it to peer into the hearts of distant galaxies and identify the subtle but telltale signatures of smaller, growing black holes. Recent discoveries are already beginning to reshape the debate. Webb and other observatories are now finding a growing number of these faint, active galactic nuclei at high redshifts, objects that would have been completely invisible to previous telescopes. Each new discovery adds weight to the idea that black hole accretion might have been a far more common and widespread phenomenon in the early universe than we ever thought. This doesn't necessarily mean quasars were the sole heroes of reionization, but it strongly suggests they played a more significant and complex role than simply being rare beacons. They might have provided the hard, penetrating X-ray radiation that helped heat the intergalactic medium to those unexpectedly high temperatures, or they could have been crucial in ionizing helium much later on. The emerging picture is not a choice between galaxies or quasars, but an intricate cosmic partnership where both classes of objects, from the brightest quasars to the faintest dwarf galaxies, contributed in different ways and at different times to the Great Awakening, a symphony of light sources whose full orchestra we are only just beginning to hear. But if quasars were the brilliant outliers, the true bedrock of reionization likely rests on a foundation of objects so ancient and elusive that they have never been seen. This brings us to the profound enigma of population 3 stars, the hypothetical first generation of stars that theorists believe were the true pioneers of light. Their name comes from a simple classification system. Population 1 stars, like our Sun, are metal-rich and common in the disks of modern galaxies. Population 2 stars are ancient, metal-poor relics found in galactic halos and globular clusters. But population 3, they would have been the primordial ancestors forged from the pristine hydrogen and helium that emerged from the Big Bang, utterly devoid of any heavier elements. This lack of metals isn't just a detail, it's the key to why they were unlike any star that has existed since. In our modern universe, stars form when a cloud of gas, enriched with elements like carbon and oxygen, can cool down efficiently. These metals act like a cosmic radiator, allowing the cloud to shed heat, contract, and fragment into multiple small stars. But the first clouds had no such cooling mechanism. They could only cool through the far less efficient process of molecular hydrogen radiation. This fundamental difference in physics meant that when a primordial cloud finally did collapse, it couldn't fragment easily. It collapsed into a single, monstrously massive object. Theorists calculate that a single population 3 star could have been anywhere from 100 to 1,000 times the mass of our Sun. They would have been titans, burning at ferociously high temperatures and shining with a brilliant blue-white light that was intensely rich in the ultraviolet photons perfect for ionizing hydrogen. Their lives would have been spectacularly short, burning through their nuclear fuel in just a few million years before ending their lives in cataclysmic supernova that were unlike anything we see today. This incredible power is exactly why they are the leading candidates for starting reionization, but it's also the very reason we have never directly seen one. Their fleeting lifespan means they flickered out billions of years ago. To observe one directly, we would need a telescope capable of looking back to the very edge of the cosmic dark ages, to a time before the first galaxies had even fully assembled, and distinguish the pinpoint light of a single star from that immense distance. It is arguably the ultimate needle in a haystack challenge in all of astronomy. So instead of a direct observation, the hunt for population 3 stars has become a forensic investigation, with astronomers searching for their ghosts, the chemical and environmental fingerprints they must have left behind. One of the most promising strategies is to look for the telltale pollution from their deaths. Those pair instability supernova would have been universe-altering events, forging the first heavy elements and scattering them into the surrounding gas. The signature of a population 3 supernova would be a very peculiar chemical pattern. It would enrich a region of space with elements, but only in a specific ratio, lacking the products of multiple generations of stars. Astronomers are now using the James Webb Space Telescope to analyze the chemical composition of the most ancient, distant galaxies we can find, looking for this pristine pollution signature. Finding a pocket of gas with iron but no carbon, or a specific overabundance of oxygen, could be the long-sought indirect evidence that a population 3 star once lived and died there. Another approach is to look for their profound effect on their surroundings. A star that massive would have had a devastatingly powerful stellar wind, blasting out radiation and particles that could have carved vast cavities in the primordial gas. Some theorists suggest that the death of a population 3 star might not have left a traditional black hole remnant, but instead have completely annihilated itself, leaving nothing behind but an expanding shell of enriched gas. The environments around these stars would have been chaotic and violent laboratories, and the echoes of that violence might be imprinted on the structure of the hydrogen gas at those early times, a pattern we could detect with future radio telescopes mapping the 21-centimeter signal. The greatest challenge in this cosmic detective story is that the window for observing even these indirect effects is vanishingly small. Population 3 stars were likely only formed for a very brief period of cosmic time, perhaps only 100 million years or so. After that, the products of their deaths polluted the cosmos forever. The next generation of stars, population 2, would have formed from gas that was already lightly enriched with metals, changing the entire process of star formation and giving rise to smaller, longer-lived stars. Population 3 stars were a unique, self-terminating generation. They lit the first fires and in doing so, ensured that no star would ever be like them again. Their enduring enigma lies in this paradox. They were the most important stars for starting the cosmic story we live in, yet they are the ones we are almost certain to never see, their existence known only by the profound changes they wrought on the entire universe. Even as we grapple with the sources of light and the physics of their escape, another layer of the reionization mystery unfolds on the grandest of scales, its geometry. If the universe's transition from neutral to ionized was a patchwork process, what was the actual shape of that patchwork? Were the ionized bubbles like fine, bubbly foam, or were they colossal, continent-sized structures? This isn't just a question of aesthetics. The size and distribution of these bubbles hold the key to understanding how the first light sources were organized across the cosmos, and the emerging picture is deeply puzzling, challenging our very models of how structure grew in the infant universe. For a long time, the most sophisticated computer simulations predicted a certain kind of geometry. They suggested that reionization would begin with many small, isolated bubbles forming around the very first rare galaxies and quasars. As time progressed, these bubbles would expand and begin to merge with their neighbors, creating ever larger, irregularly shaped ionized regions. The expectation was for a wide distribution of bubble sizes throughout most of the process, a cosmic soup with bubbles of all scales. By the time the bubbles were on the verge of merging into a single, fully ionized universe, The largest ones were predicted to be on the order of tens of millions of light-years across. This is an immense scale, larger than the local group of galaxies that includes our Milky Way and Andromeda, but it's a scale that fits comfortably within our understanding of how matter clusters together under gravity. However, a powerful new way of observing this ancient era is now providing data, and it's telling a very different story. The most exciting tool for mapping this geometry is the detection of the redshifted 21-centimeter line. Massive radio telescope arrays are now listening for the faint whisper of neutral hydrogen from the epoch of reionization. The goal is to create a three-dimensional map of the universe at that time, showing us the precise shapes of the neutral regions and the ionized bubbles that punctuate them. Early results from these pioneering experiments are nothing short of startling. They suggest that the ionized bubbles were not a collection of various small and medium sizes, but were instead overwhelmingly enormous, far larger than most simulations had predicted. We're talking about structures that could span hundreds of millions of light-years, vast voids of ionized plasma so large they challenge our understanding of how matter was distributed in the early cosmos. This creates a profound tension between theory and observation. How could bubbles grow to such staggering sizes? The growth of an ionized bubble is fundamentally governed by two factors: the luminosity of the central source and the density of the surrounding neutral hydrogen. A single, incredibly bright quasar could create a huge bubble, but as we've discussed, these are too rare to account for many such giant regions. For a bubble to grow to hundreds of millions of light-years, it implies something else: an incredibly dense and clustered population of ionizing sources, all working in concert within a relatively small volume of space. It's the difference between a single powerful lighthouse and an entire brilliant city on a coast. One creates a beam, the other creates a glow visible for immense distances. The observed bubble sizes suggest that the first galaxies and quasars must have been much more strongly clustered together than our current models of galaxy formation predict. This forces a radical rethink of the cosmic web in its infancy. Our standard model of structure formation is based on the gravitational collapse of dark matter. It predicts that the first galaxies should have formed in a hierarchical way, with small halos merging to form larger ones. This process does create clustering, but the early data on bubble sizes suggests this clustering was far more extreme. Perhaps the first galaxies didn't form in every small dark matter halo, but only in the very rarest, most massive peaks of the initial density fluctuations. If these peaks were exceptionally rare, they would also have been exceptionally far apart, meaning that the few regions where galaxies did form would have been packed with an unbelievable number of sources, creating these phenomenal ionizing engines that then blew bubbles on a scale we struggle to simulate. Alternatively, the physics of bubble growth itself might be more complex. Perhaps the radiation from these first sources could travel much farther than we think through the pristine intergalactic medium. Or maybe the bubbles expanded not just steadily, but in rapid, punctuated bursts following major events like the explosive death of a population of massive stars. The implications of this geometry puzzle ripple outward, affecting everything. If the bubbles were truly this large, it means the reionization process was even more uneven than we imagined. Vast swaths of the universe would have been ionized very early on, while other, equally vast regions would have remained trapped in darkness for hundreds of millions of years longer. This uneven heating would have had a dramatic effect on the subsequent formation of galaxies, effectively creating two different cosmic environments with completely different rules for how and when galaxies could form. The giant bubbles also present a formidable challenge for the next generation of telescopes. Mapping such immense structures requires observing huge volumes of the universe, pushing our instrumental capabilities to their absolute limit. The mystery of reionization's geometry is ultimately a mystery about the fundamental architecture of the early universe. revealing a landscape that was stranger, more extreme, and more dramatically structured than our best virtual cosmos had ever dreamed. Yet the presence of metals in the early universe presents a fascinating paradox. On one hand, this pollution was a necessary step forward, the cosmic equivalent of moving from a primitive forge to a modern factory. On the other hand, it may have acted as a form of cosmic birth control, fundamentally altering the types of stars that could form and potentially putting a premature brake on the very process of reionization. This is the core of the metal pollution paradox. The first generation of stars, the monstrous population 3, were only possible because the gas was pristine. Without metals, the gas couldn't cool efficiently, leading to the collapse of enormous clouds into single, gigantic stars. These titans were the ultimate ionizing engines, producing immense amounts of ultraviolet light. But the moment they died in spectacular supernova, they seeded their surroundings with those first heavy elements. From that point on, the rules of star formation changed forever. This is where the paradox deepens. Metal-enriched gas can cool far more efficiently, which sounds like it should lead to even more star formation. But efficient cooling has a counterintuitive effect. It allows a large cloud of gas to fragment into many smaller clumps. Instead of forming one massive star that shines with a fierce, ionizing brilliance, the cloud produces a whole cluster of smaller, lighter stars. While these smaller stars are more numerous, they are also far less efficient at producing the high-energy ultraviolet photons needed to rip electrons from hydrogen atoms. A single 100 solar mass population 3 star could output more ionizing radiation than an entire cluster of 1,000 sun-like stars. So, the introduction of metals might have actually suppressed the overall production of ionizing photons by shifting the universe's star formation from a few brilliant giants to a multitude of dimmer dwarfs. The very thing that made star formation more common could have also made it less effective at lighting up the cosmos. The timing of this transition is everything, and it remains one of the most poorly constrained aspects of the entire era. Did metal enrichment happen quickly, swiftly extinguishing the population 3 stars after a brief, brilliant flash? Or was it a slow, gradual process, allowing the giants to continue forming in pristine pockets of gas for much longer? The answer would completely change the narrative of reionization. If metals spread rapidly, then the main drivers of reionization might have been short-lived, and the process would have had to rely on the cumulative but weaker output of countless smaller galaxies. If metals spread slowly, then the colossal first stars could have remained the primary engines for a significant portion of the epoch, providing a tremendous and concentrated source of power. This leads to the most puzzling part of the mystery. When we look at some of the most ancient galaxies with the James Webb Space Telescope, we see evidence of rapid and efficient star formation happening in environments that are already slightly enriched with metals. This shouldn't be possible if the metal pollution acted as a suppressant. It suggests that the relationship between metals, cooling, and star formation is not a simple on-off switch but a complex and delicate balance. Perhaps there is a Goldilocks level of metallicity, a sweet spot where there are just enough metals to facilitate efficient cooling and fuel vigorous star formation, but not so many that they completely quench the formation of the most massive luminous stars. In these special regions, galaxies could have achieved a perfect storm of conditions, becoming incredibly productive factories for both stars and ionizing photons. Another compelling resolution to this paradox involves the sheer force of the environment itself. In the densest regions of the early cosmic web, the pull of gravity was so overwhelming that it could have simply overpowered the finer details of gas chemistry. Even if metal cooling allowed gas to fragment into smaller clumps, the incredible pressure and density in these primordial hubs might have forced those clumps to merge and collapse into massive stars regardless. The physics of star formation in these extreme nurseries might have been dictated more by violent turbulence and relentless gravity than by the precise metallicity of the gas. In this scenario, the first metals didn't change the outcome. They just altered the pathway, with the end result still being the brilliant, ionizing stars that the universe desperately needed to continue its great awakening. The metal pollution paradox forces us to move beyond simple cause and effect and to see the early universe as a complex and dynamic system, where the rules of physics were constantly being rewritten by the very stars that obeyed them. This profound transformation we call reionization didn't emerge from a void. It was the brilliant, violent climax of a much longer and more subtle cosmic story, a period astronomers poetically call the Cosmic Dawn. This was the universe's true infancy, stretching from the fading echo of the Big Bang to the moment the very first star ignited. It was during this deep time that the invisible scaffolding of dark matter began to clump together, pulling faint wisps of hydrogen gas into the first gravitational wells. For perhaps 100 million years, the universe was a silent, expanding darkness, a canvas upon which the faintest seeds of structure were slowly being sown. The great mystery we now confront is the timeline of this dawn. How long did this quiet, neutral universe persist before the first starlight finally pierced the gloom? And how much longer after that did it take for that light to coalesce into the universal revolution of reionization? The gap between first light and full-blown reionization might hold the key to understanding the true nature of those first, elusive cosmic objects. Pinpointing the start of this process is like trying to find the first drop of rain in a hurricane. Our best clues come from a variety of indirect observations that all point to a single, startling conclusion. There may have been a significant lag between the formation of the very first stars and the moment their collective light truly began to clear the cosmic fog. Data from the Planck satellite, which maps the cosmic microwave background, suggests the universe was still largely neutral at a redshift of around 10, when it was roughly 450 million years old. Yet, observations from the James Webb Space Telescope are now finding fully formed galaxies at even higher redshifts, meaning they existed when the universe was well under 300 million years old. This creates a tantalizing chronological puzzle. Galaxies were clearly present and forming stars very early on, so why did it take so long for their combined radiation to initiate large-scale reionization? This delay suggests the first epochs of star formation were somehow inefficient or isolated, unable to immediately impact the vast intergalactic medium. One compelling explanation for this lag time is a simple matter of infrastructure. The universe needed time to build its first cities. The very first stars, the population 3 giants, likely formed in extreme isolation. Single, magnificent beacons separated by oceans of dark, neutral gas. Their ionizing photons, however powerful, could only clear a relatively small bubble around themselves before being absorbed. For reionization to truly begin, these isolated bubbles needed to grow and, crucially, to merge. This required a critical density of sources, a cosmic tipping point where the ionized regions overlapped and created large, connected volumes of transparent space. Reaching this critical density took time. It required multiple generations of stars to form, live, die, and enrich the gas to allow for more efficient star formation in the next cycle. It required small dark matter halos to merge into larger ones that could host more prolific galaxies. The delay, then, might reflect the time needed for the cosmic web to mature enough to support a sufficiently dense population of luminous objects to drive a universal transition. But another, more intriguing possibility is that the first stars themselves were not the efficient ionizers we imagine them to be. Our models assume these primordial titans produced a flood of ultraviolet light, but what if their incredible power was also their greatest weakness? A star 100 times the mass of our Sun has a ferociously strong stellar wind. It might have blown away the surrounding gas in its natal cloud, effectively shutting off its own fuel supply and leading to a very short, albeit brilliant, life. Furthermore, if these stars formed in especially dense pockets of gas, much of their ionizing radiation could have been immediately absorbed by the very cloud that gave them birth, never escaping to reach the intergalactic medium. In this scenario, the first stars could have been like fireworks in a thick fog, spectacularly bright, but their light quickly muffled and contained. It might have taken the death of these first stars in supernova to truly clear the local environment, blowing away the dense gas and allowing the next generation of stars to form in more open clusters where their light could stream out freely. This would introduce a natural pause, a generational gap between the first stifled light and the second wave that finally started the real work of ionization. The duration of this lag time is not just a chronological detail, it's a vital diagnostic tool. A long delay would strongly suggest that the first stars were indeed these isolated, self-limiting titans, and that reionization was ultimately finished by a later population of smaller, more numerous galaxies. A very short delay, on the other hand, would point to a universe where star formation became efficiently widespread almost immediately, perhaps driven by a surprising abundance of small galaxies from the very beginning. By measuring the precise moment the universe began to rapidly ionize, we are essentially taking the temperature of its early star-forming efficiency. This is why observatories like the James Webb Space Telescope are so focused on pushing the redshift frontier further and further back. They are not just looking for the oldest galaxies, they are trying to census them, to count how many there were at each cosmic age and measure the ionizing power they actually contributed. Each new distant galaxy discovered helps to fill in a point on this cosmic timeline, slowly revealing whether the dawn was a long, gentle sunrise or a sudden, explosive event that quickly set the sky ablaze. Yet for all our complex simulations and observations of distant galaxies, one of the most direct ways to study this era is to try and listen to it. This brings us to a mystery that emerged not from a grand space telescope, but from a small, unassuming radio antenna in the Australian outback, and its findings are so strange they threaten to rewrite the laws of physics themselves. We're talking about the 21-centimeter signal anomalies. To understand why this is such a big deal, you have to picture the early universe not as a collection of objects, but as a vast, featureless sea of neutral hydrogen gas. This gas has a natural signature. It constantly emits a faint radio whisper at a precise wavelength of 21 centimeters. As the universe expands, this signal gets stretched to longer wavelengths, and by tuning our radio telescopes to different frequencies, we can effectively tune into different cosmic eras. Mapping this signal would give us a direct, three-dimensional movie of the reionization process, showing us the neutral hydrogen fading away in real time across billions of years. It is the ultimate goal of a new field of astronomy, and the first tentative results have thrown everything we thought we knew into question. The story centers on a groundbreaking experiment called EDGES, the experiment to detect the global epoch of reionization signature. Unlike large arrays that map fine details, EDGES was designed to detect the overall average signal from the entire sky at these ancient frequencies. In 2018, the team announced an astonishing result. They had detected a deep absorption dip in the radio spectrum at a frequency corresponding to when the universe was around 180 million years old. This was the signature they were looking for, but its depth was shocking. It was more than twice as deep as the absolute maximum predicted by our standard cosmological models. According to the physics we know, this should be impossible. An absorption signal that strong suggests the hydrogen gas was much colder than it had any right to be, or that the first sources of light, likely the first stars, were far more intense than we ever imagined. It was like listening for a faint sigh and instead hearing a deafening roar. The signal was so powerful it simply couldn't be explained by our current understanding of the universe. The immediate implication was that something was dramatically wrong with our models. The most popular explanation proposed to salvage the standard model involves an interaction between normal matter and dark matter. In the very early universe, when the gas was cooling, dark matter particles, if they have certain specific properties, could have acted as a universal heat sink, siphoning thermal energy away from the hydrogen gas and cooling it down to temperatures far below what was previously thought possible. This would require dark matter to be not entirely dark. Its particles would need to be able to interact with normal matter through some force other than gravity, albeit very weakly. This is a profound proposition, as decades of experiments have searched for exactly such interactions and found nothing. If the edge's result is true, it wouldn't just change the story of reionization. It would be the first direct evidence for physics beyond the standard model, fundamentally altering our comprehension of the universe's most abundant yet invisible component. However, the plot thickens because in science, extraordinary claims require extraordinary evidence, and the edge's result has proven incredibly difficult to verify. Other experiments like Sarah's and Leda, using different instrumentation and techniques to hunt for the same global signal, have so far failed to detect it. They've looked and found nothing but radio silence where EDGES reported a monumental crash. This doesn't necessarily mean EDGES is wrong. It could mean that the signal is fiendishly difficult to distinguish from the overwhelming foreground noise of our own galaxy. The Milky Way blasts out radio waves millions of times stronger than the faint cosmic signal, and untangling the two is perhaps the greatest technical challenge in all of modern cosmology. The EDGES team employed sophisticated statistical models to subtract this foreground, and it's possible that a subtle error in this process could have created the illusory dip. Conversely, the other experiments might have calibration issues or systematics that prevent them from seeing a real signal. The situation is a stalemate, creating a deep schism and immense confusion within the field. The confusion doesn't end with the global signal. Larger arrays designed to map the 21-centimeter signal in detail, like Hera and the LOFAR telescope, are also delivering puzzling results. They are beginning to see the patchwork of ionized bubbles during the heart of the reionization era, but the fluctuations in the signal appear to be much weaker than expected. The universe seems smoother, quieter, and less dramatic than our most sophisticated supercomputer simulations predicted. This could mean that the process was more uniform than we thought, perhaps because the ultraviolet light from the first galaxies was able to travel much farther than modeled, or it could point to a different problem entirely. Perhaps the radio signals from this epoch are being smothered or scrambled on their long journey to Earth, absorbed by intervening clouds of cold gas in the later universe that we don't fully account for. Each new observation seems to answer one question while raising two more, pulling us deeper into a cosmic detective story where the clues contradict each other at every turn. The 21-centimeter window was supposed to provide a clear view of our cosmic dawn, but for now it's showing us a glass darkly, hinting at a reality far stranger than any of our theories. But to observe this faint, ancient whisper requires looking through an incredibly noisy modern sky. The radio glow from our own galaxy is millions of times brighter than the signal we seek, and untangling the two is a monumental task of statistical analysis and instrumental calibration. The EDGES team used sophisticated models to subtract this foreground, but the possibility remains that a subtle, unaccounted-for error in this process could have created the illusion of such a profound dip. Conversely, follow-up experiments that have failed to detect the signal might themselves be overlooking something. This scientific stalemate has created a deep and fascinating schism, a mystery that can only be solved by newer, more sensitive experiments, and perhaps a complete rethinking of the fundamental physics that governed our universe's infancy. The promise of a clear view into the cosmic dawn remains, but for now, the 21-centimeter window shows us a glass darkly, hinting at a reality far stranger than any of our theories. To move beyond this conflicting global signal, astronomers turn to a different and more detailed form of observation, one that focuses on the specific light of the most brilliant beacons in the distant universe. This brings us to our next profound enigma, the Gunn-Peterson Trough mystery. Imagine you are a photon of light emitted from the blazing core of a quasar, a supermassive black hole shining with the brightness of 1 trillion stars. Your journey to Earth will take you billions of years, and your path will lead you through the vast, mostly empty expanses between galaxies. But this space is not a perfect vacuum. It is filled with a sparse fog of neutral hydrogen atoms. As you travel, any hydrogen atom you encounter can absorb you if you have exactly the right energy, a specific wavelength in the ultraviolet part of the spectrum known as the Lyman alpha line. For a quasar whose light is redshifted into the visible or infrared by the time it reaches us, this absorption will create a distinct pattern in its spectrum, a series of dark lines called the Lyman alpha forest, each line representing a specific cloud of hydrogen at a specific distance. Now push this idea to its extreme. Look at a quasar so distant that its light was emitted during, or even before, the reionization era. If the intergalactic medium along its line of sight is still predominantly neutral, then you won't see a forest of individual absorption lines. Instead, you will see a complete and total absorption of all light at wavelengths shorter than the Lyman alpha line at that quasar's redshift. This creates a vast, dark blank space in the spectrum, a profound void of information known as the Gunn-Peterson Trough. The presence of such a trough is the ultimate signature of a neutral universe. Its absence, the detection of some transmitted light in that same region, is the definitive proof that the universe along that path has been ionized. The mystery is not the existence of the trough itself, but its puzzling and inconsistent behavior. When astronomers began discovering these incredibly distant quasars, they expected a clean, universal signal. They thought that at a certain redshift, around 6 or so, every single quasar's spectrum would show a Gunn-Peterson trough, indicating the universe was still neutral. At redshifts lower than that, the trough should vanish, showing the universe was fully ionized. But the universe, as always, defies such simple categorization. What they found was a baffling patchwork. Two quasars at the exact same redshift can tell two completely different stories. One might show a deep, complete Gunn-Peterson trough, its light completely extinguished by a sea of neutral hydrogen. Its neighbor in the sky at the same distance might show a clear spectrum with a detectable amount of transmitted light, proving that its line of sight has already been cleared. This is the most direct and powerful evidence that reionization was not a uniform, synchronized event. It was a messy, piecemeal process where vast regions of the cosmos could remain shrouded in primordial darkness even as others had been flooded with light for millions of years. This patchiness answers one question but raises another, even deeper one. Why is the transition so sharp in some directions? For certain lines of sight, the change is dramatic. Quasars at a redshift of 6.1 might show near total absorption, while those at 6.0 show near total transmission. This suggests that in that particular direction, the final stages of reionization happened with breathtaking speed, like a curtain being ripped away in an instant. But in other directions, the transition is far more gradual, with partial transmission persisting over a much wider range of redshifts. This sharpness, or lack thereof, is a crucial clue. A very sharp transition implies that the ionizing sources in that region were incredibly powerful and clustered, able to rapidly overwhelm and evaporate the last remaining islands of neutral hydrogen. A more gradual transition suggests a less efficient process, perhaps driven by fainter, more dispersed sources that slowly ate away at the fog over a long period. The most compelling explanation for this directional dependence brings us back to the fundamental architecture of the universe, the cosmic web. A quasar's line of sight is not random. It will pass through a specific sequence of cosmic environments, perhaps piercing the heart of a dense supercluster of galaxies in one direction, or shooting out through a vast, empty void in another. The path that cuts through a dense knot of the web would encounter a high concentration of early galaxies, all working in concert to ionize their surroundings quickly and completely. This would create a very sharp, well-defined edge to the ionized bubble, leading to the dramatic Gunn-Peterson transition we see. Conversely, a line of sight that traverses a cosmic void would tell a different story. Voids contain very few galaxies, so the ionization fronts would have to propagate over mind-boggling distances from the structures at the void's edges. This process would be slow and inefficient, resulting in a long, lingering tail of partial neutrality that would manifest as a much more gradual transition in the quasar's spectrum. The light from a single quasar doesn't give us a global average. It gives us a core sample of the universe along one specific, razor-thin line. By collecting thousands of these core samples from quasars across the sky, we are slowly piecing together a three-dimensional map of the final, frayed edges of the cosmic dark ages, revealing a universe whose reionization was not a single event, but a mosaic of countless local dawns, each with its own unique story of how the light finally broke through. Even after the cosmic fog had largely lifted and the universe was declared officially ionized, the job was far from finished. The end of reionization didn't mean the flood of ionizing photons simply stopped. It meant the universe had transitioned into a new, sustained phase, one where a pervasive but invisible field of ultraviolet radiation now bathed all of intergalactic space. Think of it not as a single flashbulb going off, but as the main lights in a vast cosmic auditorium being switched on for good. This universal ultraviolet background is the afterglow of reionization itself, the cumulative light from every star, every quasar, every galaxy that contributed to the Great Awakening, their photons now endlessly crisscrossing the expanding universe. For a long time, theorists assumed this background would be smooth and uniform, a perfectly even wash of energy, a testament to a job well done. But the universe, it turns out, is a terrible interior decorator when it comes to lighting, and the walls are anything but a single, even color. The discovery of these fluctuations came from a clever piece of cosmic detective work, focusing on an unlikely witness, the humble satellite galaxy. Small dwarf galaxies orbiting larger ones are incredibly sensitive probes of their environment. Their gravitational grip is weak, making it difficult for them to hold onto their own gas. The ability of such a galaxy to form new stars depends on a delicate balance. It needs to accrete fresh, cool hydrogen from the intergalactic medium, but that same gas is constantly being heated and evaporated by the ambient ultraviolet background radiation. If the background is too intense in a particular region, it can effectively sterilize these small galaxies, preventing them from forming any new stars and stripping away their gas, leaving them as dark, ghostly relics. By mapping the populations and properties of these tiny galaxies across the sky, astronomers began to see a startling pattern. Some regions of space seemed to be filled with active, star-forming dwarfs, while other, seemingly identical regions were populated only by dark, quiescent fossils. The only explanation was a dramatic fluctuation in the strength of the ionizing background. In some directions, the ultraviolet light was a gentle warmth allowing star formation to persist, while in others it was a scorching blast that shut it down completely. This unevenness presents a fascinating puzzle because the sources of this radiation, galaxies and quasars, are themselves clustered together along the cosmic web. Just as people are not spread evenly across a country but gathered into cities, towns and villages, so too were the engines of the ultraviolet background. This clustering alone would create natural variations in the radiation field. You would expect a stronger background near a dense supercluster of galaxies and a weaker one out in the cosmic boonies. But the observed fluctuations are far more extreme than this simple city lights model can explain. The differences in radiation intensity from one region to another are so vast that something else must be acting to amplify the initial unevenness, something that prevents the light from spreading out and smoothing itself over. The prime suspect in this cosmic mystery is the intergalactic medium itself. Even after reionization, the universe is not a perfect vacuum. It is filled with a very sparse, but not zero, population of neutral hydrogen atoms as well as clouds of slightly denser gas. While these atoms are too few and far between to reform the primordial fog, they are just enough to act as a kind of cosmic fog machine, selectively absorbing and scattering the very ultraviolet photons that make up the background. The key factor here is the mean free path, the average distance a photon can travel before it is absorbed. If the mean free path is long, photons can travel far from their source, spreading out and smoothing the background radiation into a uniform glow. But if the mean free path is short, photons are absorbed very close to where they are emitted. This traps the light, preventing it from traveling far and creating intensely bright regions near sources and much darker voids further away. The great revelation from recent measurements is that the mean free path in the early universe was surprisingly short. This means the ultraviolet background was inherently lumpy because the light couldn't travel far enough to homogenize. A galaxy sitting in a dense knot of the cosmic web would be born into a neighborhood blazing with intense local radiation from its many galactic neighbors, making its own survival a challenge. A similar galaxy born in an isolated void would enjoy a much quieter and darker existence, able to form stars in peace for much longer. This opacity effect acts as a powerful amplifier, taking the initial clustering of sources and magnifying it into the wildly fluctuating radiation field we infer from the satellite galaxies. The universe wasn't just lit by a few bright cities. It was a landscape of brilliant metropolitan centers surrounded by vast stretches of dark countryside, with the roads between them too dangerous for light to travel freely. This discovery forces us to completely rethink the late-time evolution of galaxies. The strength of the ultraviolet background in a galaxy's immediate environment became a primary factor in its destiny. A strong local background could suppress the formation of all but the largest galaxies by either photoevaporating their gas reservoirs or simply heating the gas so much that it couldn't collapse. This provides a compelling explanation for the so-called missing satellites problem around galaxies like our own Milky Way. We find fewer small dwarf galaxies than our models predict, perhaps because many of them were simply sterilized and stripped of their gas by a locally intense ultraviolet background early in their history. The fluctuations in this ancient radiation field didn't just create an interesting pattern in the sky. They directly dictated the population of galaxies we see in the universe today, a lasting imprint of the messy and uneven way the cosmos first turned on the lights. But as we map these vast fluctuations in the ultraviolet background, we begin to see their profound and lasting impact on the smallest structures in the cosmos, leading us directly to one of the most enduring puzzles in all of modern astronomy, the satellite galaxy problem. For decades, our most sophisticated supercomputer simulations of cosmic evolution have told a very specific story about dark matter. They predict that a galaxy the size of our Milky Way should be surrounded by thousands of smaller dark matter clumps or halos, massive enough to host their own small satellite galaxies. Yet when we look out at our local galactic neighborhood, we only observe a few dozen of these dwarf companions. This glaring mismatch between prediction and observation has been a persistent thorn in the side of the standard cosmological model, forcing astronomers to ask a simple but profound question: where are all the missing satellites? The answer, it seems, may be written in the searing light of the reionization era. The proposed solution is a story of cosmic suppression. Imagine one of these small, nascent dwarf galaxies beginning to form in the early universe. Its gravitational core is a clump of dark matter, and it has successfully pulled in a delicate reservoir of neutral hydrogen gas, the raw fuel for its first stars. But then, the epoch of reionization begins. A flood of ultraviolet photons from the first galaxies and quasars permeates intergalactic space. For a massive galaxy forming in a dense region, this external radiation is a minor nuisance, its deep gravitational well easily able to shield and hold onto its vast gas reserves. But for a tiny dwarf galaxy with a weak gravitational pull, this radiation is an existential threat. The energetic photons heat the gas to tremendous temperatures, dramatically increasing its pressure. This hot, high-pressure gas becomes impossible for the dwarf's feeble gravity to contain. The gas either never cools down enough to collapse into stars in the first place, or it is violently blown out entirely, photo-evaporated away by the relentless external radiation field. The dark matter halo remains, but it is rendered sterile, a dark, starless ghost forever incapable of lighting up and becoming a galaxy we can see. In this scenario, reionization didn't just clear the fog between galaxies. It also selectively pruned the cosmic tree of galaxy formation, preventing a vast population of the smallest galaxies from ever blooming. However, like all good cosmic mysteries, the plot quickly thickens. The devil, as always, is in the details of timing. For this suppression mechanism to perfectly solve the missing satellites problem, reionization had to occur at a very specific cosmic moment. It needed to happen early enough to affect the vast number of small halos before they could form a significant number of stars, but not so early that it would also suppress the formation of the larger dwarf galaxies we do see today, like the Large Magellanic Cloud or Fornax. When astronomers run simulations that incorporate this effect, they often find that the timing is slightly off. If reionization happens too late, too many small galaxies form and survive, and the problem remains. If it happens too early, it might even suppress the formation of the brighter dwarfs we know exist, creating a new problem. Many models struggle to find a single reionization timeline that neatly erases the thousands of predicted tiny satellites while perfectly preserving the few dozen larger ones we actually observe. This timing tension suggests that reionization alone may not be the sole culprit. It is likely the leading actor, but it had a supporting cast of other destructive processes. The internal fury of the first stars themselves, their stellar winds and supernova explosions could have played a crucial role in expelling gas from these small halos from the inside out, a one-two punch that combined internal and external feedback. Furthermore, the dark matter itself might be part of the answer. If dark matter is warmer than in our standard cold dark matter model, meaning its particles were moving faster in the early universe, it would naturally form far fewer small halos to begin with, reducing the scale of the missing satellites problem before reionization even had a chance to act. The current frontier of research involves untangling this web of effects, running incredibly detailed simulations that combine the global ultraviolet background from reionization with the local violence of supernova and the fundamental properties of dark matter. The goal is to find the precise cocktail of suppression mechanisms that can reproduce the exact population of satellite galaxies we see orbiting our own Milky Way and our neighbor Andromeda. This intricate puzzle beautifully connects the largest scales of cosmology, the universe-wide process of reionization, to the very smallest scales of galaxy formation, showing how an event that played out across billions of light years ultimately decided the fate of the tiniest galactic companions in our own celestial backyard. Just when we think we have a handle on the timeline, a single protracted shift from darkness to light, an even more radical idea emerges, one that turns the entire narrative on its head. What if reionization wasn't one event but two? This is the core of the double reionization hypothesis, a provocative and controversial theory suggesting our universe didn't awaken just once, but experienced a false dawn, a stutter step of illumination that flickered on and then off again before the final, permanent lights came on. Imagine a distant campfire struggling to catch in a damp forest, flaring up brightly for a moment before the moisture snuffs it out, only to be successfully rekindled later with better tinder. This concept posits a first, aborted attempt at cosmic enlightenment, a preliminary phase that was ultimately crushed by the universe's own overwhelming weight of neutral gas. The mechanics of this hypothetical false start are as fascinating as they are speculative. The story begins not with galaxies, but with the very first truly pristine structures to form after the Big Bang. These wouldn't be galaxies as we know them, but vast, dark matter halos collapsing earlier and faster than our standard models predict. Within these rare, massive halos, the first generation of stars, the monstrous population Roman III giants, could have ignited astonishingly early, perhaps when the universe was a mere 100 to 200 million years old. Their collective ultraviolet radiation would have begun carving out the first small bubbles of ionized plasma in the surrounding hydrogen fog. For a brief, glorious period, reionization might have begun. But these pioneers were operating in an incredibly hostile environment. The universe was still much smaller and denser then, packed with a suffocating amount of neutral hydrogen. The ionizing photons from these first stars had an extremely short mean-free path. They couldn't travel far before being absorbed. The process was simply too inefficient, like trying to dry a soaked sponge with a single match. This is where the hypothesis gets its name, recombination. Recombination is the process where a free electron is captured by a proton, reforming a neutral hydrogen atom. It's the opposite of ionization. In this early, dense universe, the rate of recombination within the partially ionized bubbles would have been ferociously high. The moment a star stopped producing photons when it died its spectacularly short life, the relentless pressure of the surrounding neutral gas would have rushed back in, causing the ionized bubble to collapse and recombine almost instantly. The universe, in effect, would have healed its wounds, swallowing the light and plunging those regions back into darkness. This early, failed attempt would have left almost no direct trace, its brief ionization erased as if it had never happened at all. The cosmos would then have had to wait for a second wave of sources, one that emerged later from more robust and numerous galaxies, to finish the job permanently. So why would astronomers entertain such a seemingly outlandish idea? The motivation comes from several puzzling observations that a single-phase reionization model struggles to explain. One of the strongest hints is the surprising existence of supermassive black holes at incredibly early times. We have now observed quasars powered by black holes with masses of over 1 billion suns, shining when the universe was less than 700 million years old. For a black hole to grow that massive that quickly is a monumental challenge for astrophysicists. The double reionization hypothesis offers a potential solution. That first, aborted phase of star formation would have created a population of massive seeds, black hole remnants from the first population Roman III stars. These seeds would have had a crucial head start, hundreds of millions of years of extra time to accrete gas and merge with each other before the second, permanent reionization began. They weren't starting from scratch, they were starting from a foundation laid during the universe's first, forgotten attempt at dawn. Furthermore, this idea could help resolve the tension between the different timelines we get from the cosmic microwave background and the quasar spectra. The Planck satellite's polarization data suggests a relatively late and rapid reionization, while studies of the Lyman alpha forest show evidence of a much more prolonged and patchy process. A two-phase model elegantly reconciles this. The main event, the one that finally stuck, could have been the later, quicker event that Planck detects. Meanwhile, the earlier, failed phase would have contributed to the patchiness and complexity seen in the quasar absorption lines, leaving behind a subtle, lingering unevenness in the hydrogen distribution that the second wave of radiation had to contend with. Of course, the double reionization hypothesis remains highly speculative, firmly on the fringe of mainstream cosmology. The biggest hurdle is a complete lack of direct smoking gun evidence. That first wave of stars and their subsequent collapse would have been so brief and so localized that their signal is likely buried deep beneath the noise of later cosmic events. Detecting it would require a telescope capable of seeing farther back and with more sensitivity than anything we currently possess. However, it serves a vital purpose in science. It pushes the boundaries of our imagination and forces us to question the simplest story. It reminds us that the universe is capable of false starts and dead ends, that its history may be far more complex and circuitous than our tidy models suggest. Whether true or not, the hypothesis challenges us to look deeper and to consider that the cosmic dawn may not have been a single sunrise, but a series of struggles between light and darkness, with victory hanging in the balance until the very end. While we've been listening for the faint radio whispers of hydrogen and searching for the brilliant beacons of the first quasars, another, more subtle mystery has been emerging from the darkness, one that requires us to measure the total light output of the entire cosmos. This brings us to the enigma of the cosmic infrared background anomalies. Imagine trying to measure the total light from a distant city at night. You could count up all the individual streetlights, car headlights, and illuminated windows. Now, imagine you finish your count and discover that the overall glow from the city is significantly brighter than the sum of all those individual sources. You'd be forced to conclude that there's an entire population of lights you missed, perhaps countless faint, unseen bulbs illuminating every alleyway and backyard. This is precisely the confounding situation astronomers find themselves in when they look at the universe's total background light, particularly in the infrared. This diffuse glow, known as the cosmic infrared background, is the collective light from every star and galaxy that has ever existed, its wavelength stretched by the expansion of the universe into the infrared part of the spectrum. It's the fossil remnant of all the energy produced through cosmic history. By pointing our most powerful telescopes at dark, seemingly empty patches of sky between known galaxies, we can measure this faint, all-pervading radiance. When astronomers did this with instruments like the Spitzer Space Telescope, they made a startling discovery. The total amount of light in this infrared background significantly exceeded the amount that could be accounted for by adding up the light from every known galaxy we've ever catalogued. There's a glaring surplus, an excess of infrared light that comes from somewhere beyond the known universe of stars and galaxies. This missing light represents one of the biggest discrepancies in all of cosmology, and many theorists believe its origins are tied directly to the reionization era. So, where is all this extra light coming from? The most compelling explanation points to a hidden universe of faint, distant galaxies that are simply too dim for our current telescopes to see individually. We've already discussed how these unseen legions of dwarf galaxies might be the missing workforce behind reionization. The infrared background anomaly is their collective ghostly signature. Think of it as a cosmic crowd roar. From a distance, you can hear the roar of a massive crowd even if you can't make out any single voice. Similarly, the combined light from trillions of these faint, high redshift galaxies creates a detectable background hum, even though we cannot pick out any one of them from the noise. This explanation fits beautifully with the photon budget problem. These are the very sources that could have provided the extra ionizing radiation we've been searching for. However, the plot thickens because the amount of excess light is so immense that it forces us to consider even more exotic possibilities. Perhaps the first stars were not just efficient, but unimaginably prolific, forming in numbers far greater than our models allow. Or maybe there's an entirely new class of astrophysical object we haven't yet dreamed of, something that produced a tremendous amount of infrared radiation in the early universe. Some have even ventured into the realm of new physics, suggesting that the decay of hypothetical exotic particles, like certain types of dark matter, could have released energy that contributes to this pervasive background glow. While this remains highly speculative, the sheer scale of the anomaly means that no potential solution can be entirely ruled out. The James Webb Space Telescope is now at the forefront of solving this mystery. Its primary mission is to peer deeper into the infrared universe than ever before, and it is specifically designed to detect these faint, distant galaxies that have until now existed only as a theoretical necessity. Every time Webb points its mirror at a seemingly empty patch of sky for a deep field image, it's not just looking for pretty pictures, it's conducting a cosmic census. By counting the faintest, most redshifted galaxies and measuring their collective light, astronomers hope to finally close the gap between the known sources and the total infrared background. If Webb finds enough of these faint galaxies to account for the excess, it will be a monumental confirmation of our basic model of structure formation. If it doesn't, if the anomaly persists even with Webb's incredible vision, then we are truly facing something new, a fundamental gap in our understanding of how the universe assembled its first sources of light and what those sources actually were. The infrared background is more than just a diffuse glow. It is the integrated ledger of all cosmic activity, and its unexplained balance is a direct challenge to our account of the universe's youth. Yet for all the power of starlight, the story of reionization would be incomplete without its most enigmatic and powerful characters, the first black holes. Their origins are shrouded in the deepest cosmic secrecy, and their explosive growth during this era presents a puzzle so profound it challenges our understanding of physics itself. This is the black hole seeding mystery, a question that asks not just how these gravitational monsters formed, but how they managed to achieve such staggering sizes in what amounts to a cosmic blink of an eye. Astronomers are investigating three primary suspects for the seeds of these first black holes, each with its own compelling physics and profound implications. The first and most conventional model points to the dramatic deaths of the first stars, the population Roman 3 giants. A star hundreds of times the mass of our Sun would have lived a short, violent life before collapsing under its own immense gravity. In many cases, this collapse would not be a quiet fade to black, but a catastrophic implosion that leaves behind a black hole remnant. These stellar mass black holes, perhaps tens or even 100 times the mass of the Sun, would have been scattered across the early cosmos like scattered gravel, the smallest possible seeds from which gigantic structures could grow. The challenge with this model is time. To grow from 100 solar masses to 1 billion in less than 1 billion years requires an almost insatiable and constant feast on surrounding gas, a feeding frenzy that pushes the limits of known physics. This difficulty has led to the second, more extreme model, direct collapse black holes. Imagine a scenario where an entire massive cloud of pristine hydrogen gas, rather than fragmenting into many stars, collapses directly into a single, monstrous object. This wouldn't form a star at all, but a supermassive black hole seed in one breathtakingly rapid step. These seeds would be colossal from birth, starting their lives not with a mass of 100 suns, but with a mass of 100,000 suns or even more. This head start would make the subsequent growth to supermassive proportions far more manageable. The conditions for this direct collapse are incredibly specific and rare. The gas cloud must be vast, pristine, and must be prevented from cooling and fragmenting, often requiring an intense external source of ultraviolet radiation to keep the gas hot. If these conditions were met even occasionally in the dense early universe, they could have planted the seeds for the quasars we see lighting up the cosmic dawn. Then there is the most exotic contender of all, primordial black holes. This theory ventures beyond the standard astrophysical processes and into the realm of the universe's first fractions of a second. It proposes that in the extreme density and turbulence immediately following the Big Bang, random fluctuations could have collapsed in on themselves, spontaneously forming black holes of virtually any size. These wouldn't be the remnants of dead stars, they would be fossils of creation itself, woven into the fabric of space-time from the very beginning. A population of primordial black holes with the right mass range could have been present from day one, simply waiting for the universe to expand enough for them to start accreting gas and growing. While this idea elegantly solves the timing problem, it remains highly speculative, as no definitive evidence for primordial black holes has ever been found. The urgency of this mystery is driven by the astonishing observations from the James Webb Space Telescope and other observatories, which are now finding fully formed supermassive black holes at redshifts previously thought impossible. We are seeing quasars, blazing cores of galaxies powered by black holes weighing over 1 billion solar masses, shining when the universe was less than 700 million years old. For a black hole to grow that massive that quickly is a monumental challenge. Even if it fed continuously at its maximum possible rate, a theoretical limit called the Eddington rate, it would struggle to reach such sizes. This has forced astrophysicists to consider truly radical ideas. Perhaps these first black holes were not limited by Eddington accretion and could consume gas in super Eddington bursts, gulping down matter in violent, chaotic feasts. Or maybe they grew not just by eating gas, but by frequently merging with other black holes, a rapid consolidation of power that allowed them to snowball in size with breathtaking speed. Their role in reionization, therefore, is a double-edged sword. On one hand, a bright quasar is an unmatched engine of ionizing radiation. It floods its surroundings with a torrent of high-energy ultraviolet and X-ray photons, capable of carving out immense ionized bubbles in the neutral hydrogen far more efficiently than a galaxy full of stars. They were likely the first truly powerful beacons in the darkness, the cosmic blowtorches that initiated the clearing of the fog in their immediate vicinities. On the other hand, their influence could be destructive. The intense radiation from a quasar can heat the gas in its host galaxy and beyond to extreme temperatures, effectively shutting down star formation by preventing the cool gas from collapsing. Furthermore, the incredible energy output can drive powerful winds that blow the galactic gas supply clean away, starving the galaxy of the fuel it needs for future growth. A growing supermassive black hole can thus act as both a creator and a destroyer, illuminating the cosmos while simultaneously sterilizing its own home. The black hole seeding mystery is therefore not an isolated puzzle. It is central to understanding the balance of power in the infant universe and how the most extreme objects ever to exist shape the cosmic landscape we inhabit today. Amid the chaos of the first stars and the flood of ionizing radiation, another, more subtle force was stirring in the early cosmos, one that would weave its way through the gas and galaxies, shaping them in ways we are only beginning to understand. This is the mystery of the cosmic magnetic field, an invisible architecture that permeates the universe, guiding the flow of gas, shaping the birth of stars, and channeling cosmic rays. But where did these magnetic fields come from? Were they imprinted on the universe in its first moments, or were they forged in the violent astrophysical cauldrons of the Reionization era itself? This question is not just a footnote in the story of cosmic dawn. It is a fundamental puzzle that challenges our models of how structure formed and how the universe evolved from a smooth, featureless plasma into the complex web we see today. The possibilities for their origin fall into two broad and deeply intriguing categories. The first is that magnetic fields are primordial, a relic from the universe's very inception. In this scenario, these fields were generated during a phase of rapid expansion in the first fraction of a second after the Big Bang, through exotic processes involving phase transitions or quantum fluctuations. If this is true, then a faint, weak magnetic field would have been present everywhere from the start, woven into the fabric of spacetime itself. This seed field would have been incredibly uniform, a subtle background hum of magnetism that existed even before the first atoms formed. The alternative is that magnetic fields have an astrophysical origin. This theory suggests that the first magnetic fields were generated locally by the first cosmic dynamos, the turbulent motions of plasma in the first stars, supernova explosions, or the accretion disks around the first black holes. These processes could have created small, localized magnetic fields that were then stretched, twisted, and amplified as they were blown out into the intergalactic medium by stellar winds and supernova shocks. Distinguishing between these two origins is incredibly difficult because the observed effect. A magnetized universe looks the same in both cases. The magnetic fields we detect today in galaxies and galaxy clusters are strong and complex, but they have had billions of years to evolve. Tracing them back to their initial seeds is a monumental task. The reionization era is the critical missing link. It was during this period that magnetic fields, whether primordial or astrophysical, would have been caught up in the largest scale flow of matter and energy the universe has ever seen. As the first ionizing radiation flooded out, it would have carried with it the magnetic fields from their sources, injecting magnetized plasma into the vast intergalactic voids. The expansion of ionized bubbles would have acted like a cosmic loom, weaving these fields into the large-scale structure of the cosmos. The impact of these fields on the reionization process itself is a subject of intense and growing interest. Magnetic fields are not passive observers. They exert pressure on ionized gas, influence how it collapses to form structures, and can even affect the propagation of the ionizing radiation itself. For instance, in the dense, turbulent environments where the first stars were born, magnetic fields could have provided crucial support against gravity, slowing down the collapse of gas clouds and potentially altering the initial mass function of the very first stars. Did magnetic fields help create more massive stars, or did they foster the formation of smaller, more numerous ones? The answer could change our calculations for the entire photon budget of reionization. Furthermore, magnetic fields play a vital role in the feedback processes that shaped early galaxies. The powerful jets and outflows from active black holes are thought to be collimated and accelerated by magnetic fields. These outflows were responsible for distributing the first heavy elements and for heating the gas in the interstellar and intergalactic medium. The strength and geometry of the magnetic fields present would have directly influenced how far these winds could travel and how much energy they could deposit into their surroundings. A more magnetized early universe might have seen more efficient and widespread heating, potentially explaining the unexpectedly high temperatures we measure in the intergalactic gas long after reionization ended. The frustrating and fascinating challenge for cosmologists is that our current simulations of the reionization era largely ignore magnetic fields, not because they are unimportant, but because their origin is so uncertain and their physics so complex to model. Including them requires making a choice about their initial strength and configuration, a choice that is essentially a guess. This means our virtual universes are missing a key ingredient, a hidden variable that could be orchestrating the behavior of the cosmic gas in ways we haven't anticipated. To truly model the era accurately, we need to understand this invisible component. The quest to find the origin of cosmic magnetic fields is therefore not an isolated puzzle. It is about completing the physics engine of our universe, adding the final lines of code that will allow our simulations to finally produce a cosmos that looks exactly like the one we observe around us. Yet as we marvel at this cosmic transformation from opaque to transparent, a deeper and more specific puzzle emerges, one that challenges our very understanding of how light traveled through this evolving universe. This is the transparency transition puzzle, a mystery that centers not on the overall clearing of the fog, but on how that clearing happened at different wavelengths of light, fundamentally altering our view of the cosmos in ways we are only now beginning to comprehend. Think of it not as a single light switch being flipped, but as a vast cosmic dimmer board with countless sliders, each controlling the transparency for a specific color of light. The most crucial of these sliders controlled the fate of a very special wavelength known as the Lyman alpha line, and its journey from complete absorption to brilliant emission tells a story that is far more complex and mysterious than anyone ever anticipated. To understand why this specific wavelength is so important, we need a quick primer in atomic physics. A neutral hydrogen atom has a unique fingerprint. It is very efficient at absorbing light at one precise wavelength in the ultraviolet part of the spectrum, the Lyman alpha line. Before reionization, any photon of this wavelength trying to travel through the universe didn't get far. It was almost instantly absorbed by the first neutral hydrogen atom it encountered. This made the pre-reionization cosmos completely opaque to Lyman alpha light. It was a prison from which these photons could not escape. But as the first stars and galaxies began to ionize the hydrogen around them, they didn't just create bubbles of empty space. They created zones of incredibly hot ionized plasma that was transparent to this specific wavelength. Within these bubbles, Lyman alpha photons could now travel freely. The moment a Lyman alpha photon, emitted by a young hot star in a distant galaxy, reached the edge of its local ionized bubble, however, its fate was sealed. If the bubble was small and the surrounding universe was still largely neutral, the photon would be immediately absorbed upon hitting that neutral wall. But as the bubbles grew and merged, these photons could travel farther and farther until eventually they could journey across the entire cosmos. The universe was becoming transparent specifically for Lyman alpha light. And that change was not gradual or uniform. It was a dramatic, regional transition that happened at different times in different places. This transition is what allows astronomers to use the Lyman alpha line as a powerful cosmic probe. For a galaxy in the process of reionization, its Lyman alpha emission is a direct report on the conditions of its local intergalactic medium. If we observe a distant galaxy and see strong Lyman alpha light coming from it, we can be confident that it resides in a large, well-developed ionized bubble. Its light has managed to escape its local neighborhood. If we see little to no Lyman alpha emission, it suggests the galaxy is still trapped in a neutral region, its signature light stifled by the surrounding fog. By censusing the Lyman alpha properties of thousands of galaxies at different redshifts, we can effectively map the progress of reionization in 3 dimensions, watching as the universe slowly becomes transparent to this specific wavelength. It is one of our most powerful tools for charting the end of the cosmic dark ages, but this is where the mystery deepens and the puzzle earns its name. According to our best models, we should see a very clear and dramatic transition. At high redshifts, when the universe is largely neutral, no galaxies should show strong Lyman alpha emission. Then, as we look at slightly lower redshifts corresponding to the peak of reionization, we should start to see a few galaxies with this emission, their bubbles having grown large enough to allow some escape. Finally, after reionization is complete, the majority of galaxies should display strong Lyman alpha lines. This clean, statistical trend is what simulations predict. However, when astronomers actually point their telescopes at the most distant galaxies, they find something baffling. They are discovering galaxies at astonishingly high redshifts deep within the epoch where the universe should be almost entirely neutral, that are shining brightly with Lyman alpha light. These galaxies are not just faintly emitting, they are among the brightest Lyman alpha emitters we have ever seen. It's as if we're finding brilliantly lit lighthouses in the middle of a dense, impenetrable fog bank. According to our understanding, their light should be completely absorbed. The fact that we can see it at all suggests that our timeline is wrong. Our models are incomplete, or something truly strange is happening in the early cosmos. This startling observation forces us to consider several radical explanations. The first and most straightforward possibility is that reionization happened much earlier in some regions than our global models suggest. Perhaps these surprisingly bright galaxies reside in the hearts of the most overdense knots of the cosmic web, where galaxies formed earlier and in such incredible numbers that they collectively ionized a vast local bubble far ahead of the universal average. In these cosmic metropolises, the transition to transparency could have occurred hundreds of millions of years earlier than in the quieter suburbs and empty voids of the universe. Their light isn't breaking through a global fog. It's traveling freely through a colossal local clearing that we, from our distant vantage point, are peering directly into. A second, more thrilling possibility is that the physics of these early galaxies themselves is different from anything we see later. Perhaps their intense Lyman alpha emission isn't just leaking out through a clear channel, but is being powerfully amplified by the unique conditions within them. Maybe enormous outflows of gas driven by supernova or black hole activity are blowing long, low-density tunnels through the neutral hydrogen, creating evacuated corridors that allow the light to escape like a bullet through a barrel. Alternatively, the sheer force of the starbursts in these galaxies could be so immense that they are effectively punching their own local bubbles into existence faster than our models can account for, becoming their own architects of transparency. Then there is the most speculative idea of all, that our understanding of the Lyman alpha line itself needs revision. Could there be unknown physical processes at work in the early universe that alter how this light interacts with hydrogen? What if the primordial gas had a different temperature or density that changed its absorption properties? Or perhaps the light is being transferred in a more complex way, scattering off of moving clouds of gas in a manner that effectively helps it find gaps in the neutral barrier, a process that could make galaxies appear brighter in this line than they should be. Each of these explanations challenges a different facet of our standard model, pushing us toward a more nuanced and complicated view of the universe's great unveiling. The transparency transition wasn't a simple curtain drop. It was a performance with unexpected solos and dramatic spotlights appearing on stage long before the main house lights were scheduled to come on. Yet, even after the final ionized bubbles merged and the universe was declared fundamentally transparent, the cosmic cleanup was never truly complete. Scattered across the cosmos like isolated islands that survived a global flood, stubborn pockets of primordial neutral hydrogen held out against the relentless tide of ultraviolet radiation. These are the enduring neutral islands, the final holdouts from the cosmic dark ages, and their continued existence billions of years after reionization ended presents a fascinating puzzle. Why did some of these ancient gas clouds survive unscathed while the vast majority of the intergalactic medium was permanently transformed? The answer lies in understanding the ultimate cosmic game of hide and seek, where dense clouds of gas found ways to shield themselves from the brilliant light that filled the universe. The most common survivors are known as Lyman limit systems. The name comes from their defining property. They are clouds of neutral hydrogen so dense that they become completely opaque to photons at the Lyman limit, the specific energy required to ionize a hydrogen atom. Think of them not as wispy fog, but as thick cosmic brick walls. When a wave of ionizing radiation encounters one of these systems, the outermost layer of hydrogen atoms absorbs the photons and becomes ionized, but this very process creates a protective shell. The ionized outer layer acts like a sacrificial barrier, shielding the dense, cool, neutral gas in the cloud's core from the incoming radiation. These systems are the foot soldiers of persistence, surviving through a combination of their own density and a simple physical principle. It's difficult to ionize a cloud from the outside when the outside is constantly being ionized first, creating a protective buffer. Even more impressive are the damped Lyman alpha systems. These are the true titans of neutral gas, colossal reservoirs so incredibly dense that they can completely absorb the Lyman alpha line, leaving a broad, damped trough in the spectrum of any quasar whose light passes through them. These are not mere clouds, they are the direct progenitors of modern galaxies, vast rotating disks of pristine gas that contain more mass than many of the galaxies we see today. Their survival strategy was one of sheer, overwhelming scale. Their gravitational pull is so strong that they can hold onto their cool gas even when bathed in the external ultraviolet background. Ionizing a damped system is like trying to evaporate an ocean with a hairdryer. The energy required is simply too great for the diffuse intergalactic radiation field to provide. They are cosmic fortresses, their immense mass serving as their primary defense. But these enduring neutral islands are not distributed evenly across the universe. They are found preferentially in the deepest, darkest voids, the most underdense regions of the cosmic web. This peculiar distribution is the second part of the mystery. Why would the most effective shelters be in the emptiest places? The answer is a beautiful and counterintuitive consequence of cosmic structure. The process of reionization itself was driven by the clustered nature of the first galaxies and quasars. They formed in the densest knots of the dark matter web, and it was from these bright nodes that the ionizing radiation flooded outward. The densest regions were therefore the first to be ionized, and they were subjected to the most intense and prolonged radiation, leaving little chance for any neutral gas to survive. The radiation in these regions was local, powerful, and relentless. In contrast, the vast cosmic voids were the last places to be reached by the ionization fronts. The radiation that finally trickled into these empty expanses was the diluted, exhausted remains of that initial flood, having traveled billions of light years from the nearest clusters of galaxies. It was a faint, weakened glow, lacking the punch to evaporate the dense clouds that had quietly formed there. Furthermore, the voids themselves offered a form of environmental protection. With far fewer galaxies, there were far fewer nearby sources of ionizing radiation to threaten any neutral gas that had managed to coalesce. A damped Lyman alpha system in a void is like a secluded island nation. It survives not because of its own strength alone, but because the world's superpowers are too far away to bother with its conquest. These surviving pockets are not random. They are a direct fossil record of the final, sputtering stages of reionization, marking the places where the wave of ionization finally lost its momentum and energy, leaving behind the last untouched remnants of the primordial universe. So as we reach the end of our journey, what have we truly learned about the Cosmic Reionization Era? We've ventured through 25 profound mysteries that together paint a picture not of a single solved equation, but of a vibrant, chaotic, and deeply puzzling chapter in our universe's story. From the identity of the first light sources and the baffling photon budget shortfall, to the late reionization of helium and the universe's unexpected fever, we've seen how feedback loops could both build and destroy, how dark matter may have been the invisible architect, and how the topology of ionization might have been a bizarre outside-in process. We've grappled with the Lyman continuum escape problem, debated the quasar contribution controversy, and hunted for the ghosts of population 3 stars. We've explored the puzzling geometry of enormous bubbles, the paradoxical role of the first metals, and the potential lag time of the cosmic dawn. We've tried to decipher the anomalous 21-centimeter signal and the inconsistent stories told by the Gunn-Peterson trough. We've mapped the fluctuating ultraviolet background and its role in the missing satellites problem, and we've even considered the radical idea of a double reionization. We've looked for the missing light in the cosmic infrared background and pondered the origins of the first supermassive black holes. We've investigated the invisible influence of cosmic magnetic fields, the unexpected early transparency to Lyman alpha light, and the enduring mystery of the neutral islands that survived it all. This isn't a simple story with a clean ending. It is a symphony of questions, each mystery a movement in the grand composition of the universe's awakening. Cracking these codes requires more than any single telescope or wavelength of light. It demands a united front across the entire electromagnetic spectrum. Radio telescopes like the Square Kilometre Array will map the neutral hydrogen in 3 dimensions, listening for the 21-centimeter whisper from the dawn of time. The James Webb Space Telescope, with its unparalleled infrared eyes, is already sensors taking the faintest galaxies and probing the escape of their ionizing radiation. Future missions like the Laser Interferometer Space Antenna might even detect the gravitational waves from the mergers of those first supermassive black holes, while next-generation observatories will continue to push the redshift frontier further back than we ever thought possible. This is a golden age of multi-messenger astronomy, where data from radio waves to gamma rays are pieced together to form a coherent picture of this elusive era. The next decade promises revelations that will undoubtedly rewrite our textbooks. Each new observation is a piece of the puzzle, and with every new piece, the image of our cosmic origin becomes slightly clearer, yet often more surprising. The story of how our universe grew up, how it lit its first fires and cleared its throat of primordial fog, is a narrative that is still being written. And this is where the conversation turns to you. Which of these 25 mysteries captures your imagination the most? Are you captivated by the hunt for the very first starlight, or does the enigma of the invisible dark matter architect pull at your curiosity? Perhaps the sheer scale of the photon budget problem or the bizarre concept of a double reionization leaves you wondering. Share your thoughts in the comments below. Let's continue this exploration of the cosmos together, because the greatest chapters in this story are those we have yet to